I forgot to record again. So we must so we first clarify how Laplacian, the estimate for Laplacian operator implies the estimate for the Cauchy-Riemann operator, and then we just state our main theorem today. That is, consider the complex linear, real linear and smooth Cauchy-Riemann operator, and then we will have the Fredholm property for them. This relies on the relation between df and df star. So the last two statements concerning about the exact relations. And so from 2 and 3 directly implies 1. Not directly, it implies 1. That is, if we assume 2 and 3, then we will easy to prove the first statement. And if we assume that 2 and 3 is true, this will imply that we have the first first claim. So once the second and the third statements are true, then we will have the LR of sigma and E tensor with the zero form of sigma is isomorphic or is equal to a direct sum of the image of df star of df direct sum the kernel of df star. So in order to do this, we should set eta belongs to the intersection of the image of df with the kernel of df star. But note that here, the image of df is a subset of wk minus 1 q of sigma E tensor with T101 sigma. So it does not readily imply that this will be included in LR, but in this case, we will see that yes, this does not imply this, but we will see that since we have eta belongs to kernel of df star, this tells us that df star eta is 0. But note that df is elliptic, and this implies that df star is also elliptic. So this tells us that we also have the corresponding elliptic estimate. That is, we have this. So we have elliptic estimate. That is eta, the W1P norm of eta over some compact subset is bounded by the LP norm of eta on a larger subset, and plus the norm of df star eta of the LP norm. But here it cancels, it vanishes to 0. So we have the eta of W1P norm is bounded by the LP norm of eta. So here we just replace P by R. So this tells us that eta belongs to W1R local of belongs to yes, sigma and E tensor with T101 sigma. But then we can use the elliptic bootstrapping. That is, we can raise the regularity of eta by just iteratively imply this inequality. Then we tell us that eta is smooth. since we know that eta is smooth, because eta is smooth, this implies that so the kernel of df star is a subset of, in fact, it's a subset of LQ sigma and the E tensor with T01 sigma. It should lie in any LQ space. It should lie in any LP space. So so we can talk about the intersection with image and kernel, the image of df and kernel of df star. But then we know that eta is equal to df of some Cauchy. Since eta is smooth, we both said Cauchy is also smooth. Then we know that yes. Then we will know that yes. So since but the second statement tells us that once eta is in the kernel of df star, we will have the integration of eta with df zeta for any zeta equals to the L2 norm of df star eta and zeta, but this is 0. So this tells us that the integration of eta over so we can choose zeta to be the zeta 0 here. So eta pairing with zeta 0 in the integrate over the volume form is 0, and this implies that eta, the L2 norm of eta is 0. So eta is 0. So this tells us that their intersection is. So this tells us that intersection is trivial. So and we have another similar claim that the LQ norm of sigma, or no, again LR, and E tensor with T01 sigma must equal to, okay, we should prove another one at first. LR or LQ, I think this is LQ. Yeah, it should be LQ. And we have proved that the kernel is in fact lying in LQ, so there will be no problem here. And in order to prove that it is in fact a direct sum, we just consider the annihilator. That is, suppose eta is an element such that eta is annihilator of the image of df direct sum with the kernel of df star. We know that LQ is a Banach space, and in fact it is reflexive. So eta is orthogonal to this, means that eta belongs to LR by this representation theorem. Then we know that then we know that eta should annihilate the space of the kernel, the image of df. This tells us that eta belongs to the kernel of df star by statement 2. But since eta is but then eta annihilates the kernel of df, star, this implies that we just pick the same eta in kernel of df star, then we will have eta over the volume form is 0. This tells us that eta is 0. So this proves the first claim that LQ should be the direct sum because what? Yes, because any linear functional that vanishes on the direct sum is identically 0. And since yes, so it remains to see that this is closed. But we know that the kernel is automatically closed. And for the image, we know that we know from the elliptic estimate that we know that if we view df as W1p of WKPF, yeah, of sigma and T01 sigma tensor with E, no, E, just E, to WK minus 1p of sigma T01 sigma tensor with E is bounded, then we can just consider if let it be x and let it be y, and we can consider x to x direct sum with y with identity direct sum with df. So and it embeds into the wk minus 1p norm k minus 1p of sigma and T01 sigma tensor with E. So no. So we have x to y and with the inclusion I plus df. And we know that this operator satisfies the elliptic estimate that is wk minus kp norm of u is bounded by c times the kp norm of dfu. So we just write x and plus the inclusion. And we know that by Riemann-Roch, I is compact. So this tells us that the operator I plus df it has a closed image. And it's injective. This should be the norm of y. And we know that I is yes, and also we have I, since we know that I is compact, this tells us that the operator I plus df has finite dimensional kernel. It comes from the standard results in functional analysis. So I will omit the proof here. And if you want me to give a proof, I can try to give a proof next time or here. So I think there are also yes. So we know that the image of df is closed, and the direct sum is also closed. So we know that so this tells us that LQ is just the direct sum of the image of df plus direct sum with the kernel of df star. Here we should also Yeah. Here we also apply the Hahn-Banach theorem because yes, with trivial reasons. I think once you want to give a proof, then you will meet with the case when you must apply Hahn-Banach theorem. Yeah, and another similar result is LQ space of sigma with values in yes, the LQ space of the sections is isomorphic. Here is just E. It's isomorphic to the direct sum of image of df star and the kernel of df. The proof is completely similar. So now we are going to see that why they are Fredholm, but this follows directly from these two decompositions because we know that the image of df is we know that from the result that it has finite dimensional kernel and closed image. We know that image of df star is closed, and its direct sum complement the kernel is finite dimensional. So we know that from this, we know that the co-kernel of df star is also finite dimensional. And from the above statement, we know that co-kernel of df is finite dimensional. So this tells us that df and df star are Fredholm operators. With index of df just equal to the dimension of the kernel of df minus the dimension of the kernel of df star, and the index of df star is just the dimension of kernel of df star plus the dimension of co-kernel of df star of the kernel of df minus. So this tells us that the sum of their index is 0. Now it remains to show that the Fredholm index is independent of the choice of Kp and the choice of the almost complex structure. But we know that independent of the choice of Kp, Kq, since kernel of df and the kernel of df star are also consists of smooth functions. So for any P, K, and Q, they are when we compute the kernel of df and the kernel of df star, we find that they are all smooth functions, so the dimension will remain all the same. So here we should say smooth sections. And it is independent of the choice of almost complex structure because if we let lambda to j lambda a sequence having a family, or to say a smooth path of almost complex structures, on sigma with lambda not greater than or equal to 0 and less than or equal to 1, Then we have what is I going to say? Oh yes. Then we can reparameterize I, the closed unit interval, so that lambda to j lambda, the family is constant near 0 and 1. So this means that for some epsilon 1 and some epsilon 2, the almost complex structures are all the same. And in order to do this, and in order to see the choice of almost complex structures is independent of the family of Fredholm operators. No, in order to see that the Fredholm index is independent of the choice of almost complex structures, we just consider the product manifold. So we product with a unit interval, and we put the tangent bundle back to some vector bundle over this product manifold, and then we consider an almost complex structure. Here it must be almost complex because the dimension of the product manifold is odd, so that there will be no complex structures. And we consider an almost complex structure J, the grade J, on the upper J on P star of T sigma. I think it should be I. Yeah. Then we have such that I restricted to T times sigma is equal to J of T. Then we know that I is smooth because the family is smooth. And we know that in this case, we have, pick a connection. We make it to be complex linear. Or we can say we just pick a Riemannian, we just pick a emission structure on the pullback bundle. So that pick a complex linear connection like A on the pullback bundle, and with the connection we can tell about parallel transport. Gives the bundle isomorphism. Phi lambda. I think it should be two variable lambda 0 to lambda 1. It maps T sigma, P star T sigma restricted to lambda 0 cross sigma to the bundle T star P star T sigma restricted to the product of with lambda 1 and sigma. And in fact, we know that they are all isomorphic to T sigma with just different complex structures, with just different almost complex structures. So we know that since we have this bundle isomorphism, we will directly see that T sigma 0, that is with complex structure 0, is isomorphic via phi 0, 1 to T sigma 1. And we know that any two on the manifold sigma, any two almost complex structures, it is a classical result in symplectic geometry that any two almost complex structures can be connected by one such path. This is a linear algebraic result. That is, we just apply the linear algebra to see the space of almost compact structures is a convex space. So that any two such compact structure can be connected by one such path. We should say it is compactable. Since here we have the volume form and we should compatible with the volume form, but if it is not compatible, then it does not make sense that we consider the family of almost compact structures. Yeah, so here we should say compatible. So then we know that we pick connection. We pick an admission connection on E. And we consider the corresponding, yes, Cauchy-Riemann operator d lambda with respect to the given complex structure. Then we say that d lambda composed with phi lambda. No, it is phi 0 to lambda. Phi 0 to lambda. From WKP of sigma T01 sigma tensor with E. No, sigma E to WKP sigma T01 sigma tensor with E. That is, we map any section C to d lambda C, but this is one form. This is section. This is one form with values in. Yes, this is a 101 form with values in E. So we just compose it with phi lambda, and here we impose the J0. So yes, we should say it is lambda to 0. Lambda to 0 or 0 to lambda. I think this should be lambda to lambda 0 to lambda, and so this is a one form, so we can just apply the composed with phi lambda, phi 0 lambda. Yes. So this is a Fredholm operator. It is obvious because the phi 0 lambda is a bundle isomorphism. So they will not contribute to any of the Fredholm index of the operator. So the composition is again Fredholm, and it's a family of Fredholm operators. Then we know that a family of Fredholm operators, then we know that a continuous deformation of Fredholm operators has the same Fredholm index. This tells us that finally this tells us that this tells us that yes, so the Fredholm index of d lambda are all equal to the Fredholm index of d0. That is, the Fredholm index of the Cauchy-Riemann operator df is independent of the choice of the almost complex structures. So this proves 1. But we still need to cheat with the second and the first statements that if eta, that's the corresponding adjoint properties for eta. And we know that in fact, if we view this as a L2 norm, and this tells us that the df of eta is equal to C. It should not be star. There should not be a star. There should be a star, but we at this time we do not know what this means. So it's just df eta in the weak sense. No, it should be df star. Yes, from the explicit expression in order coordinates, it should be df star. So we have df star equals C in the weak sense, and we want to see that if eta has regularity. This is our main problem. So this involves again the elliptic estimate. So now let's just proof of the first and the second and the third statement involves elliptic estimates for the Cauchy-Riemann operator. So from the relation, let us copy here. Copy. How to copy? Okay. So let's copy the statement. What happens? Okay, so let's just copy. I think we use it is more convenient to use the L2 norm to write this integration equals to the C. This is zeta for all zeta belongs to WKP KQF sigma and E. Yeah. So we are going to see that eta is has regularity and that zeta has a boundary conditions. So first comes an observation that in local coordinates, so in local coordinates we just have let the volume form be lambda squared ds dt, and we have the coordinate uz where u is a subset of h, and then we just set z equals to z plus it, and then we just write df as d bar plus a, and in fact it will equals to, and in fact we can write the emission connection like nabla s equals to ds plus phi, and nabla t equals to dt plus psi, where they are all real linear matrices. Because what I'm going to say, yes, because in this case we can set E to be trivial by choosing a unitary frame, and then the space of all, and we are considering the space of all, how can I say? Yes, and we are considering the space of all 0, 1 forms. So so it can become the just, how can I say? Okay, so E is trivial, so we have the phi and the psi are matrices. Now we want to write the eta, write Cauchy in local coordinates. So df of Cauchy, where zeta, where zeta is a 0, 1 form, it should equal to ds zeta. So df is equal to 2/1 with the connection ds zeta minus or plus. I think this is plus I dt zeta, and with the differential form ds plus I dt. But here, since we are doing in local coordinates, we are always with ds plus I dt, so we can drop it and write it as only a number. So then the differential form, then the operator is just an ordinary differential operator on C. Then this tells us that so the L2 norm, the L2 inner product of eta and df zeta is equal to the L2 norm of eta and 2/1 ds zeta plus I dt zeta, and we just expand it as ds zeta plus dt I dt zeta plus phi zeta plus psi times I zeta, the L2 norm. So yes, then we just then we need to do some then we need to change phi and psi to the right hand side, and the ds plus idt remains. So we just have 2/1 eta ds zeta plus idt zeta, the L2 norm plus 2/1. But here this is just phi star eta plus psi star I eta. Although we have assumed the volume form to be lambda squared dsct, but in this case, eta and Cauchy, eta and zeta are all 0, 1 forms. So in this case, the L2 norm of them, I mean, yes. So in this case, the adjoint is just given by the real adjoint of these matrices. And for on the on the other side, this is just C pairing with zeta. So if we want to expand the volume form as DSCT, then we just equal to lambda C and zeta DSCT. So we drop the DSCT, and okay, there is some notational notation problem with yeah, just L2. So we know that this is because yeah, maybe I should write here. Yeah. So finally, we expand the volume form into DSCT. Or here, because they are all 0, 1 forms, so the pairing is just eta wedge the hot star operator of these things, and so we when we do the joint, we just directly make replace phi by this joint. So we obtain this. So this gives us no, I think I should drop the 201. So there will be no. So this tells us that eta pairing with this will equal to lambda square C minus phi star eta minus psi star I eta pairing with C, the L2 norm. This tells us that in the weak sense, we always have ds minus I dt of eta equals to lambda square C minus phi star eta minus psi star I eta for in a weak sense. But here we should treat with some we should treat with integral indices. That means that because this belongs to wk minus 1p k minus 1q, and eta belongs to lr, so the whole thing belongs to ls, where s is the minimum of q and r and is greater than 1. So then we will have so we just apply this with ds plus idt, apply both sides by ds plus idt. So this will be ds plus idt in a weak sense, lambda squared C minus phi star eta. I think there is something wrong. Yeah, yes, this is plus, because we have a conjugate, and yes, it should be plus. But that makes no problems with the estimate. So this is the Laplacian. And so we just apply the elliptic estimate for Laplacian to obtain that the local norm of eta is bounded by the global norm of lambda squared C plus minus phi star eta plus psi star times I eta, the LS norm. And in fact, we know that this is bounded, and also plus eta of LS norm. But we know that sigma is compact. So this tells us that any LT will embed into LS for t less than s by Holder's inequality. So this so we have obviously the LS norm of eta is finite. So this tells us that eta it belongs to W1S local. In fact, it belongs to W1S sigma. But now we should, but our required result is eta is belongs to W1Q. So we must have eta. So we have two cases. One is S is less than Q, and the second is S equals to Q. So this is clear. So when S is less than Q, we must do more things. The first one is that if S is greater than 2, then eta will lies in LQ because it will embed into any LP spaces with integral index greater than S. And Q is obviously greater than S, so eta will be in LQ. And another is S is less than 2, then we will have eta in LP for S for P greater than or equal to S, but bounded by 2S, quotient by 2 minus S. So we must clarify the relation between Q and S. But we know that, yes, but this is greater than 2. So this tells us that eta will lie in L2. And then, because eta lie in L2, and so the thing is that if Q greater than 2 or Q less than 2, yes, we should make we should consider more cases. If Q is greater than 2, then it follows that lambda square times this minus phi star eta plus psi star I eta is in L2, and the elliptic estimates tells us that they belongs to W12, and they will embed it into LQ. And in this case, eta is that automatically belongs to LQ. Yeah, because of companions. So in any cases, eta belongs to LQ. Eta belongs to W1Q. This is our first regularity, and we should see eta must belongs to WF1Q. But this is because if we choose UI tends to eta in W1Q, and each UI is smooth. Now we know that since U is a subset of H, we can give an extension of U to U tilde that we have introduced in the previous talks, that this is U, and we just apply the U tilde. And then we consider the matrix R, which is equal to identity on the first R variables and -1 on the last R n variables. And then we can consider the if U is a function from U to R2n, then we can consider extension of U s minus t ft with t less than 0 equals to R times U s minus t. That is, we just give a reflection. Okay, so in this case, for any such smooth functions, we can just make a construction of 2 over 1 ui st plus r times ui s minus t. And in this case, we know that eta I maps S0 into the boundary condition. So it will satisfy boundary condition. And we know that in this case, eta I tends also to eta in W1 S norm. It is W1Q. norm. So we apply the trace theorem that we have introduced before. No, I think I forgot to introduce the trace theorem. Yes, I forgot to introduce the trace theorem. So the trace theorem implies that eta I tends to eta on the boundary in the set with u or us ui. I think is u tilde in LQ norm. In any cases, we can make it embed into LQ norm. So this tells us that no, in any LP for some p, it is enough. And this tells us that eta S0 will belongs to the boundary, to the total real subbundle for almost every S. And this is just the boundary condition. And once we know that eta is in WF1Q, we can just apply, we can just use elliptic bootstrapping. That is when eta is in WF1Q, eta is in WF of LQ, then we can consider d alpha eta, which is in LQ, and satisfies. No, I should write d alpha and satisfies the given estimate, given relation. And this will tell us that so d alpha eta must belong to W1Q for any eta, for any alpha. This tells us that eta will belong to WKQ, WL plus 1Q, F. And finally, we know that because we have a restriction of for Cauchy. So where is my theorem? Okay, here. So we have a restriction for Cauchy. So we must have since we have this restriction for Cauchy, the upper bound for the this is a difference index should be k. So this implies that W eta must in KQF, and then it should be weakly differentiable. So this tells us that df star eta is 0 by local computation. So this proves our main theorem because we have then established all the things. So we should state what a trace theorem is. Trace theorem is a result that concerns the boundary of some of the differential operator, the boundary of a solution to the differential operator. It states that if omega is a subset of Rn, a domain with good boundary condition, so here we do not need a proof, so we do not need to specify what this good boundary condition is. And so that and there is an extension. There is a KQ extension operator E from omega to Rn to the whole Rn, and this is easy to achieve if we know the extension theorem. So, and since we want to consider the boundary, we must consider the extension. So, and let M and let k is greater than 0 and p greater than 1. Then we have and q is greater than or equal to p, but bounded by n minus 1 of p and n minus np, n minus kp. Then we have if kp is less than 2, the case kp greater than 2 is trivial because greater than 2 is trivial because we know that in this case they are automatically smooth, or to say weakly differentiable. So the boundary has an obvious estimate. If kp is less than 2, then we have the similar boundary estimate, that is wkp embeds wkp of omega embeds into LQ of the boundary of omega. That means that if a function is kp on the region, then it will be LP on the boundary. Here we need an extension because we need the value on boundary to make sense. And second is that if kp is equal to 2, then we have wkp omega embeds into LQ of boundary omega for any q. But here we are dealing with the boundary on the whole Rn, and in this case we only have this boundary, and this is H, and we do not need to extend it to the whole upper half plane. So we can just consider the intersection of this region with the boundary of H, and we can just make a reflection. This is the obvious extension operator, and it can achieve to any kp for any k and p by say yes. So I think this easy example can be found in Evans. Okay. So then we can apply the trace theorem to estimate the boundary. So in W1Q, so the limit in W1Q norm will imply the limit in LQ norm, and LQ norm will imply the almost every S we have the boundary condition, and eta will satisfy the obvious boundary condition. Okay, this is all I want to say this 1.2 hours, 1.3 hours. So are there any questions?